Alright, so video mark scheme for the synoptic part of the test, starting with periodicity. So it's asking you to determine the difference between the sodium plus ion and magnesium 2 plus ion in terms of its size. The explanation is probably easiest to do first, so that you understand why the smaller ion is what it is. So it comes down to both shielding and nuclear charge. Sodium and magnesium are in the same period, and therefore they have the same shielding. So the distance between the nucleus and the outermost electron is exactly the same in both ions. Also, it comes down to nuclear charge, and magnesium has more protons in the nucleus than sodium does. Because they have the same shielding, because magnesium has more protons, magnesium 2 plus attracts the outer electrons more, and therefore is the smaller ion. So your answer for the smaller ion should be Mg2 plus. So that's the first question there. Hopefully that fully explains exactly what you need to put in there. Moving on to the second part, write an equation to represent the first ionization for sodium. This comes back to right back at the start with atomic structure. So what you should be writing here is that sodium in the gas phase splits into sodium plus as a gas plus an electron. So it's just removing that outer electron from sodium in order to form a singly positive charged ion, everything in the gaseous state. Continue with the theme of periodicity. On the next page it does ask you to talk about the ionization energy of period 3 elements. This is just the graph that we're used to, and it asks you to initially look at elements 12 and 16, so magnesium and sulfur. Magnesium has a slightly higher ionization energy than sodium, drops down at the next point because aluminium's outer electron is in 3p, and then it continues upwards, and then it should drop again at sulfur. The remainder of the question does ask you to explain why that drops down between phosphorus and sulfur. So you've now got to explain why it's slightly lower. And this comes down to, again, those 3p electrons. So the electron configuration for phosphorus ends 3p3, and for sulfur it ends 3p4. Now, because there are 3p orbitals, when you look at the 3p4 of sulfur, it is the first time that electrons pair up in the 3p orbital. Because electrons are negatively charged and you're putting two electrons within a very close distance to each other, the electrons repel each other, also commonly known as spin pair repulsion. And therefore the electrons are easier to remove. And that's the level of detail that you need to include in order to get all of the marks on that question there. Question 2 does involve you filling in a Born-Haber cycle. The idea is that you've got to write the formula for each line, including state symbols. The state symbols seem to be a little bit of a problem for some people, or potentially writing in the wrong thing. First idea is that we have to look at the first arrow, at what reaction is taking place. So this arrow, which we won't highlight there, so it's this arrow here that we're looking at first. And this is the enthalpy of formation of potassium oxide. So that is things in the standard state forming 1 mole of potassium oxide solid. So in this case you need 2K, and its standard state is a solid, plus a half O2 as a gas. That is the first line there. Beyond that, we have to look at 2 different processes which start to build towards forming the 2 ions, which allow you to do the enthalpy of lattice dissociation, so ultimately getting to these ions up here. The first thing is that you should atomize the sodium, so it becomes 2K as a gas plus a half O2 as a gas. Notice we haven't changed anything to the oxygen at all, it's only the potassium that's changed, because we're making 2 moles of potassium as a gas. When we come to the calculation later, you do need to multiply this line by 2. Once we've done that, the next logical step is that you're going to atomize the oxygen, so it becomes 2K as a gas plus plus 1 oxygen as a gas. You don't need the 1 there, but that's just to show you how many atoms you're making. Because we're only making 1 atom of oxygen, we're not going to multiply that line by 2. However, the next stage, you'll notice that we are taking 2 electrons off the potassium ion atoms to form the 2 ions. Because you've taken the electron off 2 atoms, you will ultimately need to multiply this arrow by 2 at the next stage. So that there gets you 3 marks just for writing out the equations. Moving on, the next part asks us to use the data in the table to calculate the enthalpy of lattice dissociation of potassium oxide. So lattice dissociation here is splitting the solid into its gaseous ions. Looking back at what we need, that arrow is this one here. So the easiest thing to do is to start at this arrow and work around to this arrow. So to start off with, we're going to look at the enthalpy of formation. So if we scroll back down to the data, enthalpy of formation of potassium oxide is minus 362. Because that arrow is going in the opposite direction, we are going to write it as plus 362 and change the sign. Then, next arrow is the atomization of potassium. Remember, you've got to do that twice. So we're going to add on 2 lots of the atomization of potassium, which if we have a look at the top there is plus 90. So we're going to add on 2 lots of 90. Then, the way we've got it written is that you are going to atomize the oxygen. Remember, we only have to do that once for 1 atom of oxygen. So we're going to add on 2, 4, 8. Next process is 2 lots of the first ionization energy of potassium. So again, we're going to have to multiply this one by 2. So we're going to plus 2 lots of the enthalpy of ionization of potassium, which is 418. Then we're going to look at the electron affinities of oxygen. So the first one there, because the arrow is going in the same direction, minus 142. And then second electron affinity of oxygen is plus 844. When you combine all of those different numbers together, you should get the answer for your calculation. And if you've done it correctly, you should get an answer of 2328. So that's your answer there. And remember, the units, if you need to state them, will be kilojoules per mole. Next question is a comparative question between the enthalpy of potassium oxide and sodium oxide. So the first thing to note is that the formula of potassium oxide is K2O from the question above, and the formula of sodium oxide will be Na2O. So the only difference between those two ionic compounds there are that the sodium, or the group 1 metal, sodium and potassium, is the difference between the two. The oxide effectively does not matter. So it's basically comparing the two properties of sodium and potassium. Well, the first thing is sodium is smaller sodium and potassium have a positive ion, so not 2+. They both have the exact same charge, and for that reason sodium has a higher charge density and therefore how the Na2O has stronger ionic bonds. Okay, in the next question, we're starting to look at the thermodynamics topic where you're going to be using Gibbs free energy. And first question asks you just to write down the equation that shows the relationship between these three terms. Hopefully by now everyone's aware that you should be able to recall delta G equals delta H minus T delta S. And as you can see above, that equation there does take the form of a straight line in the form y equals mx plus c. And if we use that graph, we can actually calculate a value for the slope and then start to discuss a little bit about what that actually represents. Now, in terms of the slope itself, if you have a look and make a triangle out of the information, we can use that triangle in order to calculate the gradient of the line. Now, the value at the tip of the triangle here is 43, and below that is approximately minus 22. So the difference in y values is 43 plus 22, or minus 22, which is about 65. So the change in y is 65. Along the bottom, you've got your first value, which is 240 for the first x value. Second x value is about 900. So if you take the two away from each other, delta x is 660. So if you do 65 divided by 660, that will actually tell you the value of the slope, and that comes out at approximately, so 65 divided by 660 at 0.098. So not quite 0.1, but just slightly below. And it does ask you really to try and get your value below 0.1, so you shouldn't round that at that point unless you show your work and show that you had 0.098 at some point. The symbol for the gradient is technically, because you're plotting delta G against T, the y-intercept is delta H, and the value for the gradient is equivalent to negative delta S. Or you do get the mark if you just write delta S. And the units for delta S in this case, because we've already done the conversion before the graph was produced, is kilojoules per Kelvin per mole. So that's all of the information that you need to get from the graph in order to answer that question. Moving on, it asks you to explain the significance for the reaction of temperatures below the temperature value where the line crosses the temperature axis. So in terms of the graph itself, that is any part of the line below this one here. Now, what this asks you to do is to start to consider what the values mean below that line. And so we know that below that line, delta G is less than 0, or less than or equal to 0. And when delta G is less than or equal to 0, reactions are feasible. And so below that line is where that reaction will actually take place, and above that line the reaction will not take place. And that's the answer to the question. That gets you both marks. In the second part, it asks you to suggest what happens to ammonia at 240 degrees Kelvin in order for the slope to change. Well, if you have a look back at the equation for the reaction, right at the top here, it does tell you a little bit about the ammonia, and it tells you initially that ammonia is in the gaseous state. So when it goes below that temperature, the most likely thing that is going to happen as you start to cool it down is that it's going to go from a gas to a solid. So gas to a liquid. So ammonia condenses to become a liquid. And that changes the value of the entropy. Okay, so for question 4, this question is to do with rate equations. So the idea is that in the first question, you're going to show how this data can be used to deduce the rate expression. So what it's effectively asking is for you to calculate the orders of reaction with respect to A and B. Initially, we're going to look at experiments 1 and 2. The reason for that is that experiments 1 and 2, the concentration of B doesn't change, so it stays the same in both. However, the concentration of A does change here, and that affects the rate. So, first thing is working out how much the rate has been changed and how much the concentration has been changed. So, to do that, to check, 0.36 divided by 0.12 will tell us the change in concentration of A, which is 3, and then 1.89 times 10 to the minus 3 over 2.10 times 10 to the minus 4 tells us that that is changed by a factor of 9. So, because as you triple the concentration, the rate goes up by a factor of 9, we immediately know that A is to the order of 2, because 3 times 3, or 3 squared, is 9. Working out B is a little bit more complex, so we're going to have to look at experiments 2 and 3 in this case. And this involves us setting up the equation and inputting a little bit of information that we already know. So rate equals the concentration of A squared times B to the unknown power B. And we'll do this in terms of proportionality, so we're going to just ignore K for now and look at how that affects the rate, because K is constant and therefore it's not going to be involved in the rate equation. So, between experiments 2 and 3, A doubles from 0.36 to 0.72, so we know that A is 2. For B, we can see that B halves between experiment 2 and 3 from 0.26 to 0.13. So in terms of numbers, we're going to put that in as 0.5 to the power of B. The rate, if we have a quick look, doubles from 1.89 times 10 to the minus 3 to 3.78 times 10 to the minus 3. So again, we're going to input 2 as the value for rate. And there we've got an equation that we're able to rearrange in order to find B. So 2 is 2 squared, which is 4, times 0.5 to the power of B. If you divide both sides by 4, that leaves us with 0.5 equals 0.5 to the power of B, and therefore B equals 1. So our rate equation becomes rate equals K A squared B to the power of 1. And that is how we get to our answer, and that gets us all 3 marks. Moving on, rate equation for a second reaction is rate equals K C squared D, and this time we're going to be calculating the value of the rate constant K. And to do that, all we're going to do is take the complete set of data from experiment 4. So that information is highlighted here, and we're just going to input that data into our rate equation that we have. So if we have rate equals K C squared D, we know that 7.2 times 10 to the minus 4 equals K 1.9 times 10 to the minus 2 squared times 3.5 times 10 to the minus 2. That there is the sum that we have to be able to rearrange in order to find K. So if we rearrange that, we should end up with 7.2 times 10 to the minus 4 divided by 1.9 times 10 to the minus 2 squared times 3.5 times 10 to the minus 2. And if you put that in your calculator correctly, what you should come out with is a value of 56.98, or you can get away with just writing that down as 57. And the units for this, because you've got an overall order of reaction of 3, aka you've got 2 and a power of 1, what that means is that your units for the rate constant have to be moles to the minus 2, dm to the plus 6, seconds to the minus 1. And that in itself will give you 3 marks. If you struggle with the units of rate constant, either come to see me on a Friday in order to get help on how to derive them, or you need to start memorising the table of information that allows you to calculate the units for K just from memory. Second part, we then have to use that rate constant that we've just derived in the first step in order to calculate the missing rate value. So again, we know that rate equals, and now it's 57 C squared D at that temperature. So we're going to input the values of C and D from experiment 5 in order to calculate the information. So we know that C is 3.6 times 10 to the minus 2. So 57 times 3.6 times 10 to the minus 2 squared, multiplied by our value for D, which is 5.4 times 10 to the minus 2. And hopefully, if you put it into your calculator correctly, you should get a value of 3.99 times 10 to the minus 3, or just 4 times 10 to the minus 3 moles dm to the minus 3 seconds to the minus 1. So it's only 1 mark for that because it is just a case of doing a little bit of maths. One big problem was that people got a little bit caught up in the fact that they realised that it was 3.98 and therefore can round up to 4, and then forgot the times 10 to the minus 3 and therefore didn't get that single mark there. Moving on to part D, this was very poorly answered. The main problem here was it does not want you to do any maths. It does want you to talk about what's happening to the rate in terms of what's happening to both E and if you change the temperature. The first thing is, if you double E, the rate is also going to double. So if you double the concentration of E, then rate also doubles. However, changing the temperature T will affect K. And has a much greater effect on rate. That's all you have to say for 3 marks. The first is for explain what will happen to rate if you double the concentration, and then talking about the fact that comparatively T will make a much bigger difference because it affects the value of K, and also that there are more successful collisions. And that will give you all 3 marks. Moving on to the last part, it is just a case of doing a little bit of maths again. The main point where a lot of people missed marks was from the lack of a conversion at the end, or possibly a misconception with the rearrange. So the natural log of K equals the natural log of A minus, and then it's probably easier to write it as AA over RT, and that could have been the problem where a lot of the rearrange came in. So natural log of K, as we know, is just a value. It tells us that the value of K, and it also tells us the value of A. If you take the natural log of K, so natural log of 6.51 times 10 to the minus 3, we should get a value of, hopefully if it works, negative 5.03 equals the natural log of A. Again, if you type that into your calculator, you should come out with a value of 23.97 minus, and then again we've got A over RT. In this case, A is our unknown, so we're going to leave that as that. R is 8.31, and T in Kelvin is 300. As we go through, we need to rearrange that equation. It's easily done if you take the AA over RT to the other side and add 5.03 on. You end up with AA over 8.31 times 300 equals 23.97 plus 5.03, which is 28.99, or effectively 29. So AA equals 29 times, over, try it again, times 8.31 times 300, and that will tell you the value of AA in joules. So 29 times 8.31 times 300 is 72297. And that's in joules per mole, and therefore in kilojoules per mole it is 72.3. Okay, question 4 involves a little bit of AS revision, looking at the displayed formulas and boiling points of two different alkanes. So in this case that would be octane and isooctane. If you have a look there, isooctane is this compound here. The longest carbon chain you can make is 5, if you consider this here. And you've got a couple of side chains coming off it. Now you're expected to give the IUPAC name for isooctane, and because the longest carbon chain is 5, you're looking at the main chain being pentane. And you've got a couple of side chains on here. You've got 2 on this carbon, and you've got a third here. So because the two first side chains are on the second carbon, that will be 2, 2, and the third is on the fourth carbon, so 2, 2, 4. Because there are 3 of the same methyl side chain, it would be trimethyl, and that is the name there. So 2,2,4 trimethyl pentane. So that's our first question 5. The next part asks us how octane and isooctane can be separated. Now again, this is a revision of any practical techniques that you might know. So it's a technique for separating the two, and this can be done by any type of distillation. Tends to be best to just say simple distillation, but distillation itself will do. And basically what you need to say at this point is that because they have both different boiling points, the easiest thing to do is to start heating the mixture of compounds. So we're going to heat the mixture of compounds to approximately 100 degrees. Because isooctane has the lower boiling point, isooctane evaporates and flows through the condenser, where it turns back into a liquid, or condenses, and is collected. So So it's just a little bit of analysis of something that we've done at AS and just talking through how distillation actually works in order to separate a mixture of two different alkanes. In the second part, it does talk about the use of isooctane in combustion. So isooctane still has the same molecular formula as octane, C8H18. So this really is a GCSE question. You're going to react it with O2 to form CO2 and H2O. The idea here is that you've just got to balance the equation. Remember that however many carbons you have in the alkane is the same amount of carbon dioxides that you'll form, and half as many hydrogens that are in the octane will form water, so in this case that would be 9. When you add up all of the oxygens on the right hand side, so you get 16 oxygens from carbon dioxide, you get a further 9 from water. 16 add 9 is 25. Because oxygen's O2, it's 25 over 2, and that is how you balance the equation. So that's the balanced equation there. The next part asks you to talk about how a catalyst works in preparation for a look at a catalytic converter. So there's 2 points that you need to mention here. One is that you have the alternative reaction pathway. So that's what the catalyst provides, and that alternative reaction pathway has a lower activation energy, which means that the reaction can happen faster because more particles have an energy equal to or greater than the activation energy, and therefore there's more successful collisions. But none of that needs to be mentioned. It is just those 2 points there that get you the 2 marks. The next question does require you to write an equation to show how two pollutants react together in a catalytic converter. This is something that you do need to memorise and understand. So you've got to have nitrogen monoxide and carbon monoxide. Those are the 2 reactants that it tells you about in the question. When they react together, you do form CO2, which is less harmful, and nitrogen gas, which is inert. So it's a case of balancing this equation at that point. What I would recommend doing is doubling the nitrogens first to balance those. At that point, you've got 3 oxygens. If you double the CO, that gives you 4 oxygens, 2 carbons, and then you can double the CO2 in order to balance the equation. Finally in this question, so we're talking about the different catalysts that are used in catalytic converters, and you've got the terms a very thin layer on a honeycomb ceramic support, and effectively you've got to use both of those pieces of information in order to get the both marks. So the reason it's used in a thin layer is because the catalyst is expensive. So you use a thin layer in order to reduce the cost. Secondly, it's used on a honeycomb ceramic support to maximise surface area. And what that does is make sure that the maximum amount of gases that pass over the catalytic converter react together. So those 2 points again there will get you those 2 marks. Lastly, you've got oleic acid here, which is another hydrocarbon. It does tell you that isooctane can be made from oleic acid, but that isn't really relevant to the question. Basically, it's just wanting you to identify a reagent that can be used as a chemical test to show that oleic acid is unsaturated. So, saturated meaning no double bonds, unsaturated meaning there is a double bond there. Whenever you test for an alkene, you're going to use bromine water or Br2 aqueous, and the observation you'll see there is that it will go from orange to colourless, or that it decolorises. Any of those 2 phrases there will get you both marks. So that's what you have to put for that last part of the question there. Okay, final question. This is to do with chemical tests. I know a lot of people haven't done a lot of revision on these chemical tests, so hopefully this will explain exactly what's going on. First question asks you to distinguish between butanol and 2-methyl propan-2-ol. What you have to identify here is that butanol is a secondary alcohol, whereas 2-methyl propan-2-ol is tertiary, so one will react and the other won't when it is exposed to potassium dichromate with an acid. So acidified potassium dichromate is your reagent. You need to put the acidified bit in, otherwise you do fall foul of losing a mark there, but you can continue to get the other two. So the observation with butan 2-ol, because it's secondary, it can be oxidized. It will go from orange through to green to show that it's been oxidized from a secondary alcohol to a ketone. And finally, the tertiary alcohol can't be oxidized, so there is no change. And that will get you all 3 marks for that question there. Further down, we've got propane. This is effectively a repetition of the question on the previous page, and again you should be using bromine water to test for the unsaturated double bond. Observation with propene, there will be no change because it's an alkane, and the observation with propene, it will go from orange to colourless, or that it decolorizes the bromine water. Either of those will do as your answer. For aqueous silver nitrate and aqueous sodium nitrate, the difference between the two is the positive ion present. So you've got Ag plus and Na plus as your 2 different ions. Now, you can try and test for each one, but the easiest thing to do here is trying to test for the silver ion. Remember that silver ions do form precipitate with any halide ion. So the reagent that I would recommend, sodium chloride aqueous or hydrochloric acid aqueous, either one will do. With the silver nitrate you will see a white precipitate of silver chloride, whereas with sodium nitrate you will see no visible change. And finally, with aqueous magnesium chloride and aqueous barium chloride, you've got a couple of options, but the barium one tends to be the one that is more memorable. Barium chloride contains the barium ion, magnesium chloride contains the magnesium ion, so you're testing between the two. To prove that the barium ion is present, you need to form that precipitate of barium sulfate. I would recommend using H2SO4 aqueous in order to make that precipitate occur. With magnesium chloride, remember that magnesium sulfate is fully soluble, so you will see no change, whereas barium sulfate is insoluble, so you will see a white precipitate form. And that is it.